So let's talk about the linear model. So the general linear model, I think you guys probably could guess what the general linear model was from simple linear regression. That all we do is add terms, right? So here was the, say, linear part of regression to the origin with the error was the regression to the origin version of linear regression, and we might add an intercept. But the general linear model just adds these extra terms, and of course there is, there is an intercept embedded in there, in that perhaps one of these let's say ji's, if it's just perfectly constant, right? If it's just one, then that term would be an intercept. And we can write the general linear model as this way, so we don't have to write a bunch of pluses out. Okay? And so how could we get estimates? Well, we could do least squares and just try and minimize the distance between the observed responses and the predicted responses given the linear model squared, and treat each one of those squared residuals equally and try to minimize the sum of the squared distances. That would be reasonable. And then, just like in linear regression, under a correct additive model with Gaussian errors, the least squares criteria also winds up being the maximum likelihood estimate. And we're not going to show that. You can show that if you'd like. And notice linear, by linear we mean linear in the coefficients. If we include x1 squared, for example, as a regressor, that really is just another x, right? That really is just x. We just happen to square it in the notation. What we really, if we were to put it into a computer program, we would just put in the squared versions of x's, and the computer program wouldn't know that they were squared, right? What's really meant by linear is linear here in the coefficients. So anything that's linear in the coefficients is a linear model. So in this case, we've just squared it. So we could have a model that says y equal beta 1 sine x, right? Where sine, I mean the trigonometric function sine. That's still fine, where this is still just a model y equal to beta 1 z, where z is the, say, plus error, where z is sine x. If you sine a vector and then put it into the computer versus just put in z, the computer doesn't know the difference, right? So what's linear, what's important about it being linear is that it's linear in the coefficients. So how do we get estimates? Well, if you really want to take a linear models class, go take a real honest-to-goodness linear models class. And what I'm going to go over is an intuitive development that teaches you what the multivariate adjustment kind of does, and it develops the estimates along the way. And again, we won't require linear algebra, we won't require calculus. I do want to remind you of this one fact. If we have a model that says, if we have a model that just said, darn it, let me just try it one more time. If we have a model that says yi equal to xi beta plus error, the regression to the origin model, the estimate, remember, worked out to be that, summation xi y divided by summation xi squared. Okay? And now let's just extend that model to two regressors, right? So that the expected value of y includes an xi1 and an xi2. And I noticed I'm sometimes confusing whether I write 1i or i1 like that, but I'm hoping you'll be able to figure that out. I'll try and correct it so that it's consistent on the GitHub repository, but when recording the lecture, I've noticed a couple of mistakes like that. I'm hoping that won't cause any confusion. So remember that, just going back to our regression estimates, when we developed least squares, remember that if mu I hat, where mu I hat was equal to xi1 beta 1 hat plus xi2 beta 2 hat, right? If mu I hat satisfied that equation for all possible values of mu I, right, mu I being right there, then we found the least squares estimates. Well, okay, and that's why we did it that way when we did linear regression, so that we could just use the same equation here. Okay, so there's our equation. Now let's just plug in to the mu I and mu I hat as to what they are. And you wind up with this statement right here, right? yi minus beta 1 xi1 minus beta 2 hat xi2 times this guy. But notice we could multiply this times this, and then this times that, and we would get two equations, summation yi minus beta 1 hat xi1 minus beta 2 hat xi2 times xi1 times a beta 1, I'm sorry, beta 1 hat minus beta 1, and then the same thing with a beta 2 hat minus beta 2 and an xi2 out there. If that term is equal to 0, and this one with the 2's on everything is equal to 0, then this whole expression will be equal to 0, okay? And so what I've done is I've simply rewritten these two conditions right here. And hopefully you'll have noticed a pattern that in general for the more than two variable case, you just have, if you have p variables, you have p of these equations. So how can we solve these equations? Well, we have two equations and two unknowns, right? We don't know beta 1 hat and beta 2 hat, but we've got two equations, so hopefully we can solve it. So if we take equation 2 and hold beta 1 fixed, right, then and solve for beta 2, we get that thing, right? Churn through the work. And then you can take beta 2 hat, which is now just written as a function of beta 1, and plug that into there, and then we get another equation. We get another equation that we can solve for beta 1, okay, because it only has the one variable. And you can rewrite that equation so that it is exactly nothing other than, so let me go back one again just to focus on this equation. Notice, what is this? Let me get it better. This. So this guy right here, this term right here, is the slope estimate from the regression through the origin model of yi equal to xi1 times beta 1, let's say, plus error. That's the regression to the origin estimate for that. And then if we were to multiply that times, I'm sorry, with the 2, it was the regression through the origin estimate for yi equal xi2 times beta 2. If we were to then multiply times xi2, we would get the predicted y from the model, yi equal to xi2 beta 2 plus epsilon I, right? So this term is the predicted y from the regression through the origin model with y and just x2. And so this is the residual from the model that only includes yi and xi2 by itself as a regression to the origin. Similarly, this right here, right, is exactly the residual for the model xi1 equals xi2 times whatever, I don't know, let's say gamma plus epsilon I, right? And then when we multiply it times xi2, we get the predicted version of xi1, and then we subtract it from xi1, we get the residual. So what we can do is we can write that equation as the ith residual if we were to have regressed x2 out of y minus beta 1 hat times the ith residual should we have regressed x2 out of x1. Okay? in both cases, regression through the origin. And we can then just solve this. And here I give the equation for how I define the residual for two vectors A given B, right? And so you get the solution beta 1 hat is this, which is, again, regression through the origin. It looks like the regression through the origin estimates, though if we were using the residuals instead of the vectors themselves. But we have this x1 here. But we're going to deal with that right now. So remember, so just from our definition from the previous page of what the residual is, this residual of x1 having regressed out x2, if we square it, right, that's this residual times this guy, just applying the definition. And I'm missing a sum there. Sum I equal 1 to n. So then distributing across the sum, we get that guy, and then we get this guy right here. Okay? But I hope you recall that when we take the sum of the residuals and we multiply them times the regressor, sum of the residuals times the regressor, that equals 0. We discussed that in regression. And if you don't believe me, plug in and convince yourself that it's true. So, so that guy, right, I'm sorry, this guy right there is 0. So what we get, just plugging into the equation, is that this guy right here is equal to summation of the residuals times xi1. And so what we can do is, just going back, we can replace this denominator right here, right? And we can replace by this equation right here, we can replace it by that. Okay, as a result, what is this? Well, this is just equal to the sum of sort of vector 1i times vector 2i divided by the sum of vector 2i squared, which we agreed was the slope estimate from the regression through the origin, where vector 1 is the response and vector 2 is the predictor. Okay, so let's summarize that. Summing it up.